you know, usually we have 14 weeks, so we started at week 3. So then they should give you, you have the right of 2 weeks. So usually when you pay for 14 weeks.
والله مسامحين يا دكتور، ما في مشكلة، متسامحين نحن.
Yeah, I mean, it's your right. Okay, let's go. Am I recorded on Teams? Just let me check, because you will be watching the record. Okay, so now I'm recording on Teams. Here we go. Last time we end up here, and we want to find y, the output. So here we have a linear system, because dealing with transfer function. Then any linear system is with multiple input. Total response is, what is the total response? Y is the sum of the individual contribution. So assuming only one input is non-zero at a time. What it means like this: my system, I'm defining it taking, for the first time, taking, so that's the first time taking d equals 0, and in second time I'm taking r equals 0, and I try to find time. I am trying to find y for each of the case. Then later I do superposition. So y, assuming this will give me y1 and this will give me y2, later than y will be equal to y1 plus y2. That's what linear system, the superposition theorem applied to linear system. Okay, based on that, so I don't want to write on using this. I better to write using my whiteboard. So then, yeah, let's start finding this y1 and this y2, assuming here d equals 0. So I'm not taking d in the first experiment. Okay. Then y1 over r, what it will be? y1 over r.
It's the forward, Doctor.
Yes, forward. So c g p
over 1 minus
1 plus loop, right?
Forward
over 1 plus loop.
صح.
What's the loop in this case? C
GP times GS.
P yes. So then you find your y1 over r. What about y2 over d? Okay, y2 over d. This I rearranged it last time in this way, so it becomes more clear. And I asked you about finding, what is this? Got it. Okay. And I asked you about finding the transfer function y2 over d. So that's your p. Okay. So then how to find y2 over p? y2 over p equal
p over
هذا
1
yes
minus مظبوط
minus
كل شيء تحت.
So
مع ال
forward over 1 minus loop. So my loop is p times gs times minus 1 times c times ga. Okay, so this equal to
دكتور
yes.
فيك بس تعيد لي حطيت minus 1 هون انت.
Yes,
block minus 1.
I will go through it. So 1 plus, just give me a second, p gs c ga.
ليه مش y2 over d مش p؟
Yeah, let me answer first the question and then I'll go back to the second. Rami, you're asking why you put here -1.
Yes.
This -1, it came from here. Okay, it's coming from here. I asked you actually to think about it for this session. This session I asked you to think about it.
Yes.
Did you think about it? And what did you find? Did you?
شهادتان ما أنا بشر يا بعد.
Yeah. So that's why I mean it needs just little bit reflection, and you will get it. That's why I asked you. I assigned it to you as assignment. Go and look at it. But what do you have here? Here you have GS.
Say feedback.
Yeah, GS minus. So here 0 minus Y2GS. So here E. What is E? What equal to what? If I ask
It's
you,
Y2 minus
E is.
Y2 minus the input دكتور.
It is minus Y2GS. Do you able to see it? My pen need to
Yes.
change. So that's E. E equal minus Y2GS. You agree? You all agree?
Yes.
If you all agree, here is my E. Here is my E.
Okay. Yes.
You get?
إيه
Just less more reflection. So then is the second question. What was the second question? Who asked it?
ليه حطيت Y2 over B مش Y2 over D؟
Yeah, Pierre, he asked why I put Y2 over.
المفروض تكون على الانبوت الاوتبوت على الانبوت مش
Yeah, you are right.
الاوتبوت.
Sorry, you are right. Yes. So this is Y2 over D, output over input. Get?
Okay.
So then, if you want in green, so here your forward is you forward from the input to the output. Okay, the forward is here from the input to the output, and the loop is the loop. Okay, you multiply everything inside. The loop is the loop. Good, so that's why here, because it's a plus, then you put minus, forward over 1 minus loop. Here, because it's a negative feedback, not a positive feedback, then forward over 1 plus loop. Okay, doing that, so now you can directly go and apply, saying to me, then y equal to y1 plus y2. Then you come here and you tell me, then y of s equal y1 of s plus y2 of s should be equal to, if you want this rule here, this is here, CGAP 1 plus CGAPGS. Hopefully I don't forget it. So CGAP over 1 plus CGAPGS. Okay, so just I get it from, so that's y1, let's check it one time, times r. Okay, times r of s plus y2 of s is p over 1 plus p gs cga times d. So then that's your y of s. And this kind of question we ask in the exam, like find y of s. Okay.
طيب دكتور، هو نحن ما فينا نطلع الواي اوف اس الا مع ان نفرقهم وتعملهم اثنين مثل ما انت عملت.
Yeah.
بس انه ما في فورمولا نطلعها
No,
من دون ما نقسمها.
the formula is forward over 1 plus loop, and you need to do the reduction as we did. So now let's take this example, and this is the example I asked in the exam last year. So similar, you see, similar to the one you have in your slide, which I explained to students. Then I asked them to go and practice this one, and they didn't practice, and I asked them about it in the exam. They didn't answer it. Not all, of course, not all of them, but some of them, they did not. So then, how to deal with this type of system? So this is my system. How many input I have in this system first?
3 doctor.
You have 3 input. Very, very nice.
3 inputs.
Right. So you have 3 inputs. Then if you want to write the output here in the system, output is V.
Superposition of 3.
Yeah. So here the output is V. Right. So then if you want V of S equal to the transfer function
N plus E plus E. صح؟
Yeah, so it is V desired. Yes, it is V desired of S
plus Dn
plus D plus
E.
plus N, right? N of S. D of S plus N of S.
V desired will okay.
Yeah, this is V desired. Okay. And here is your transfer function that you want to find. So then here you need to draw 3 block diagram for me. Okay. As here we have 2 input, D and R. So then R and D, I have R and D plus the transfer function of them. So then here in this case I have 3 input, V desired, D and N. V desired is my reference. I have disturbance and I have noise on my system. Okay, then I need to find this 3 transfer function. I need to have as I did here, you need to have 3
doctor.
Yeah, here you have 2 blocks, so you need to have 3 block diagrams to find the transfer function. Output over input, output over input, output over input in this case. Then once you find them, you get your right grade, complete grade. That's it. So usually in control, it's more likely to have this 3 type of input. You usually have noise on measurement. So assuming here you have a sensor. So usually when you measure your output that you need to feed it back here, this output most often your measurement is noisy. It doesn't come very pure or without filtered measurement. No, you have measurement, you have noise associated with measurement, and this is normal. Then take the noise into consideration, and a lot of time you have disturbance applied to your plant, to your physical system. This disturbance could be depends in the system. Okay, could be a force, could be any unwanted disturbance. Then that's my controller. Here I'm taking a value actually, so I'm not putting as in the previous one I was putting CGA. Okay, so here I was putting K constant, and here is my plant 1 over ms plus b. If you remember the 1 over ms plus b, we did it previously. That's the 1 over ms plus b. It is the transfer function of your car, 1 over ms plus b. So I take it. That's why the velocity is the output and u is the control signal. So I'm measuring the speed of the car. Okay, so I'm taking this example then here. So here your ms plus b, so you know what is your ms plus b. Okay. Back to it. So you know your ms plus b as well. Good. So let's find them one by one. So you have 3 cases, as we said. Let's do the first case. Okay, so I ask you to do the first case yourself. Then it's going to be for your exam. And do the second one yourself. And just look to the myself the third one. So then I will go with you over the third one only. And yourself you do at home the first one and the second one. Okay, get trained on them. I will do
بس دكتور سؤال.
Yeah.
هون السنسر محطوط هنحطه بالدايجرام بالبلوك دايجرام او بنتركها فاضي يعني بس
No.
فيدباك.
No, only unity feedback.
اوكي يعني ما بنعتبره قصدي بالبلوك دايجرام.
No.
اوكي.
So in this scenario I'm just taking, I want to find only the third block diagram. So I'm considering I have only noise. I have only noise. So then in this case, if you want, I'm taking
ما
0.
هيطلع.
Yes.
هتطلع بس plus and noise.
Yeah, you said Muhammad, what you said?
انه ما هيطلع الترانسفير بس هيطلع بالاخير الجواب بلس نويز الان اوف اس اعتقد.
Yeah, I'm finding this third transfer function.
دكتور بعدين بتطلع هي 1 over ال 1 plus loop minus loop.
ما في لوب عشان هي فاتة على
let's see it together. So here this is we'll do it together, the other you do yourself. So then I have k, so I'm considering d equals 0. In this case I'm considering v desired equals 0, and I will only keep the n. Okay, this v of s. So here, because block diagram better to have capital letter, and here is my noise, my input. Oh, I wrote it, I draw it confusing this way, so let me delete.
دكتور هون معنا block minus 1.
Let's see, I'm doing it with you. We'll do it together. Let's see what we will have. Okay, then here you have addition n as they did, so I didn't change anything. I just make everything else equal 0. Then I rearrange it. How do you like to arrange it? Myself, I like to arrange it in a way that I'm comfortable with. So I arrange it this way. I put my n here. Okay, I put my n here, and then my v is here. So this is my v. Then here is my minus 1 k, then 1 over ms plus b. Okay, so I'm comfortable with it this way, and this is output is v, which is here. Then this I know how to compute directly v of s over n of s. And for this one I can tell you directly that v of s over n of s equal to forward, yes, minus k over ms plus b over
1 minus.
1 minus. Nice, very nice.
minus ما في شيء.
minus the loop. What do you have in the loop? Minus k over ms plus b. Good.
Yes.
Am I fine? So then
Fine.
this is gonna be minus k if you do the derivation ms plus b plus k. So that's my v of s over n of s. It will give me this one. I'll put in red. I'll put in red. So then it is the forward. This is the forward from the input to the output. So it is minus k over ms plus b, right? And my loop is this. My loop. What do I have in my loop? I have here unity field. I have here 1. So it is minus 1 times k times 1 over ms plus b times 1. This is all what do I have in my loop. Good. Then this is your transfer function. What conclusion you could, if you look at it this way, is there any conclusion? Like if I have, let me ask you, if you have large k, how this will affect the noise? If your controller, if you take very high value of k, how this will affect your noise? Assuming k very high.
مش tends to 0.
Yeah. Yeah, right. Yeah, it said.
Yes.
Okay, so what I'm saying, like, let me take.
مش بناخد الان لفوق انه بنعملها انه بنحط ان اس ايكوال بتصير الكي بالدينومينيتور اذا tends to infinity يعني انه كبيره بتصير equal to 0.
So take
الان اس equal to 0.
Just simply don't complicate things. Just take k very high value. So if k very high value, then the other part will be neglected in front of k. Right? ms plus b will be neglected as k very high. And this will be minus 1. So then v of s approximately will be approximately equal minus n of s. Agree? If k very high, then this term is very small compared to it. Like you are saying 100 plus 1, it's okay to say 100. Or 1000 plus 1, it's okay to say 1000. Right? This doesn't affect it if k very high. Right? Then k over k, then this is negligible. K over k is minus 1. Agree? So what that means? That means so this is your transfer function at the end here, minus k. At the end, this is the third transfer function, which is minus k over ms plus b plus k, n of s. And here is d of s, the second transfer function, and here is v desired, the first transfer function. All of those will give you v of s. So now, what I'm saying is, if you are taking k very high, then v of s will be, in case of k very high, or that's how to represent very high, I want the eraser. Okay. Like that's how to say it's k very high, like this. Maybe. If k very high, then v desired of s plus, I'm not sure, this transfer function will be also dependent depends on d, but it's not my subject of interest now. Then minus, we said minus n of s, right? That's what we say here. V like becomes minus 1. This becomes minus 1. Okay, k very high, so minus n of s. That means large K will amplify the noise in your system. Like you have noise in the system, all the noise will be added to your final output. Are you paying attention in control? What's the effect of having very high gain, very high proportional controller? So then your system or your noise on measurement will be added to your output. Okay, so there is no dynamic here. There is no kind of filter here to filter the noise. So all your noise will be added to the system.
وهذا شيء مش منيح صح؟
Yeah. So then this is a drawback of taking very large gain value K. But making K very large can make your system faster and make the DC gain closer to 1. So it has some advantage, but it also has some inconvenience. Let's see them on MATLAB. Okay, just to put things on like clear. So here I'm taking the car model that you have 1 over ms plus b, but here I take the car model of your milestone. You remember it from last time. Like I'm taking this Ford car, so then when you modeled it in your milestone mini project, you get this one. Okay, and then what I did is I just added proportional controller on it. So I feed it back with a sensor equal 1, alright, with a sensor equal 1 and disturbance equal 0 and noise equal 0. There is no noise, there is no disturbance, just with the gain equal 10. Alright, so do I have anything else in some other places? Alright, so then, yeah. So let's see the simulation then. Here, all what I did, I have proportional. Let me put proportional first equal 1. So like, just I'm feeding it with a unity feedback, kp equal 1. And let's look to my output. Remember, at the input I have a final value of 10. So this is my output. If you want to see it more clear, maybe I can have 2 inputs and link my reference signal. Good. So now, so I just said like one advantage of one of advantage of increasing the proportional will actually improve the steady state. So make the system so the DC gain closer to 1 if you want, or so you will decrease the steady state error. The steady state error will be decreased. Let's see. Let's try. That's what I said. But also the system becomes faster. Like here, if you look to your steady state is around 5 seconds. Is at around 5 seconds. Okay. But if you see it's around steady state is around 5 seconds, 6 seconds. But what if I take my gain equal 5, for example? You see, I'm very close, the error is less, and also the steady state is now should be less than 5, 6. You see, it's a steady state at maybe 3, or if I take it equal 10, So what it will give me? Also, I'm very close, less steady state error decrease, but also the transient response increase, or the rise time increase, the steady state, the settling time increase if you want. So the system becomes faster. You agree? That's an effect. That's the advantage of increasing K. But I told you, pay attention. Pay attention. You have drawback of increasing the proportional. So now we are understanding the effect of proportional control. Okay, having big value of P of proportional controller will decrease the steady state error. Very nice. Will make the system faster. Very nice. But pay attention, you have drawback of it. One drawback is will amplify the noise. We just saw now in theory that this will amplify the noise. Okay, but also you have other drawback rather than amplifying the noise. So yeah, let's see now. For example, assuming I want to see the control signal. You see the control signal is up to 100 now. So also I saturate my actuator. If I increase my proportional very high, I may saturate my actuator. And this is something undesired. Okay, so you may need to apply for a short time very high voltage. So you are saturating your actuator. This is one of the drawback. They told you it will amplify the noise as well. Okay, it will amplify the noise of your system. So that's your system. Here I added a noise with a sensor dynamics. I take it one, but let me have proportional one. Apply. Okay. Then here I have white noise. I do my measurement. So here I didn't take any disturbance, and even in the previous system here I'm not studying disturbance. I'm just looking to the effect of proportional to the system. So now we have two advantage of proportional. Can you repeat them to me? What are the advantages of increasing, making K large?
Reduce the steady time.
ومake the response faster.
Make the response
Make
faster. Good. So these are the two advantages. Now you have drawback of adding. You have drawback of increasing the proportional gain.
noise.
One drawback is
Saturate
the actuator, right? You saturate
actuator.
your actuator.
Mm.
And second drawback, we said it will amplify the noise. Let's see how it will amplify the noise. Now, doing the simulation, I have small value of P in addition to noise. So my sensor, my measurement, my output measurement, in reality, it has noise. So now I add the noise to my measurement and I look to my output. That's my output, and in reality, it will look like that. So now, what if I increase the proportional? I know increase the proportional will make me close to my steady state, which is 10. Maybe you want.
بس بيصير الاوسيليشن للنويز اكبر.
Yeah, you will have, so it will amplify the noise, because that's what we saw in the theory just now. Okay, so let me take it 3 maybe and see if
أعتقد دكتور النويز منه موصول، منه مسكر، ولا هيك بس مبين عندي ما بعرف.
this
بعد
it's added
بعد ال1 بعد ال1 ما مكمل.
here.
كمل لقدام، ما طالع على الماي. اوكي هلا طلع. اوكي.
Yeah, maybe this connection problem. So you see, I'm closer to my steady state, but looks like my noise is amplified. Let's put 5 for example. So what's the effect of Your system is noisy, more noisy. What about if I take 10 and I want to, actually I can copy paste two figures together and show them to you. So like this is at 10 if you want, and I can do another one, Control C, Control V, just taking it here, and I'll take it at 2 or at 3. Just so let's do the simulation. This is at 10 and this is at 3, and compare both curve. Good. Where is the other one? Here. So you can see them. The noise is amplified. That's right. I'm closer to my steady state, and my system is faster. If you look, but I amplified with the cost of amplifying my noise, also saturating my actuator. Good. So then here there is trade-off. You as a designer, you need to make trade-off. If you have a lot of sensor, and then think about noise amplification. Is it clear? Any question regarding the effect of proportional controller? How did we find it? Good. So here you have it. I was saying here that good. What I said is like making K large. How I can write? Okay, making K large makes system faster and DC gain closer to 1. So steady state error will decrease. Both are generally desirable characteristics, but you have drawback. The actuator will saturate, and your system can amplify unwanted inputs like noise, because this is make K when K large, this will tend to -1. We demonstrated it. V over N, we find it, and tends to -1. Actually, there is one drawback also of K I didn't talk about. Okay, I will show it to you. They are saying
بس دكتور سؤال
Yeah.
هون ليش ان اس 1 بلس لوب مش هي 1 ماينس لوب؟
they get same answer as us, right?
يس بس قصدي انه لو انا 1 بلس لوب واللوب نيجاتيف انه حيطلع كمان تحت نيجاتيف.
لا لانه نحن يمكن زدنا ماينس 1 باللوب.
لا I think this is an error on their side. Let me take this out. So in our case, it is positive feedback. It is forward over 1 minus loop. Yeah, you are right.
Yes.
You are right. Forward over 1 minus loop. So this is wrong. Okay. Thank you, Ian. This is
No, well.
1 minus loop. But the answer is right, actually. Their answer is right, same as 1. So maybe they get mistake here, Professor.
Yeah.
Then one drawback I didn't talk about, which is higher order dynamics have been neglected. In our case now, we neglected the higher order dynamics, like we didn't take the dynamic of sensors, dynamic of actuators. So if those are taken, you will find one more drawback for increasing the gain K will increase the oscillation. So increasing K will increase the oscillation if your system has high order dynamics. So what I'm saying is what? What I'm saying is, let's see here. Here what I did, I included dynamics of the actuator. Usually could be this the actuator of your car. Maybe it's a motor. I'm modeling a motor. Okay, could be this is the first order model of your motor. So it's actuator dynamic. You could also have a sensor dynamic. Here I'm taking only simply dynamics of the actuator I'm considering. So now my system as a whole, my system now, it is high order system. It's not like first order now. My system is second order system. My plant, if this is my plant that I want to control, my system is higher order. It's not order 1, it's order 2 in this case. Then I'm saying for a higher order system like order 2, then increasing, you will find increasing the proportional will lead to system oscillation. So will increase the oscillation in your system. So what I'm saying is doing the simulation and verify it. Now my proportional is 1. How it looks like, that's how it looks like my system. With the dynamic of the actuator, yes, because it's second order system, I expect to have something similar. Okay, so this is my system look like that. What if I increase my gain to maybe 3? Then I run my simulation. Did you notice that that's right, my steady state decreases, but that's right, my steady state decreases, but the oscillation also increases. So steady state less, but I have more oscillation. What if I take it 10? You see, it increases the oscillation. Is it clear, or you want me to show you 2 photos at the same time so you could see it better? Yeah?
I think it's clear, doctor.
It's clear? No need to show it without.
دكتور يعني بس
Yeah.
as a sum up يعني إذا زدنا نحن دي سي جين بيصير عندنا اوفر شوت أكتر وبيسرع السيستم صح؟
Yeah. Always.
بيصير أسرع.
The advantage always there. The advantage always there. System faster and less steady state error. Less. Less steady state error.
Okay.
But you have inconvenient, like you will increase the oscillation. That's one of them. Amplify noise and saturate your actuator. So now let's look at both signal at the same time. So you can see the effect of increasing the proportional. This is a drawback. Okay, and this sum up.
دكتور بس دائما حيضل السيستم ستيبل يعني مستحيل يصير unstable صح؟
Yeah.
لو قد ما زدنا.
Yeah. It doesn't lead to unstable system. It doesn't make your system unstable. Later on, you will see in next chapter when you study the effect of integral term, you will see that the integral term can make a stable system unstable. Okay, so that it's risky to increase the integral term because it may have, even if your system was stable without control. This system, this car, it's stable without any control. Look at it, just apply input and look to the output. The system by itself is stable. Of course here because I'm having disturbance, but
yes, and we have ADC gain 6.
Yeah, system by itself, it's a stable system.
Yes.
Yeah, that's it for the effect of proportional. But I want to go a little bit more in theory about this, and this is very important to practice. Very, very important in control to understand the theory behind the advantage of K. The inconvenience of K, I just demonstrate for you this one in theory, and those we show them experimentally. and this one we in theory we validated experiment in simulation. So now those system faster and DC gain closer to 1, we saw them in simulation, but I want to show them to you in theory, how we reach there. Okay, how we reach there. Good. So is it clear what we will do now? We will demonstrate. Yeah, what we will do now? What's the step? What I'm going to go with you on what? What did I say just now? What did I say just now? Students.
Sorry doctor ما انتبهت شو قلت.
Yeah. So I repeat. I said it's very important in control. So just focus with me. It's very important in control. So it's very important for control engineer to know theoretically why increasing the gain K will lead to a faster system and less steady state error. Why? This is very important for control engineers to know in theory why. In simulation, we saw the effect of increasing K in making the system faster and let the DC gain closer to 1. But in theory, do you have an idea how we go through it? You didn't see it before, so now we'll go over it. But this is very fundamental for engineers, control engineers. Okay, let's go through it on the white paper. I will copy. I want to copy only. I wish I could copy only this one. Actually, a way to copy it is to take it from here like that and copy the image and put it here. Control V. Now I want to go with you on demonstrating. So our objective now, we want to demonstrate why. I want to demonstrate why increasing K will lead to decrease the settling time. If you want, decrease the settling time and decrease the steady state error. Right, make the system faster and make the DC gain closer to 1 if it's a unit step input. So how to go over this? So now when we are talking about it, let's assume for simplicity I don't have noise and I don't have disturbance on my system. Okay, then my system has one input, one output. So then V of S over V desired of S. Can you help me count it?
K over MS plus B
Yes.
على 1 plus
1 plus
and then K over MS plus.
MS plus B. Thank you. So if I want to do the derivation with you, then it is K over K plus B plus MS. Right? This is my system. So if I want to write it in the form A over TS plus 1, where A is how much and B how much. So then
A equal to
K equal A equal K. اوكي
Agree?
سامع.
Yeah, I agree.
So this is K plus B, and if you take, and here is K over K plus B. Am I right? Because you take
Okay.
K plus B common, you get M over K plus B plus 1. So then that's A and that's T. Good, so this is your V over V desired. And then, now look to your pole location of your plant and of your new system, Iyad. Okay, the old system has, it's my plant without controller. If I have the plant itself, has S equal minus B over M as a pole. Minus, let's assume this is here is minus B over M. This is my pole. That's why it's stable, because it's in the left half plane, in my S plane. Real, of course, and imaginary. Then, what's the pole of my closed loop system? Now, when I added the feedback, my system becomes different. So I'll put in red.
بصير minus into K plus B over M.
Yeah, so S will be minus, let's assume it is here, it's alright, it's minus K plus B over M, right?
Yes.
This is my new system.
So إذا كبرنا كتير الكي بترجع كتير لورا فبتصير neglected صح؟
Yeah, what's the conclusion you could, yeah, nice, let's analyze it.
يعني بس نكبر كتير البي بتصير البول كتير صوب الماينس انفينيتي فبتصير neglected يعني ببطل إلها effect.
Okay, yeah, you asked me this question last time, and I answered you. I will answer it again.
Yes.
Your old system, your pole was here. Remember what did I answer? I told you your pole was here. That's the old location for your pole. Now you do changement of, you change your pole. When you added your controller, you change the dynamic of your system. So now you shifted your pole from here to here. Here it's not like you accumulate the pole together and you have two poles.
Yes,
so
yes,
here
yes,
it's a
I got
difference.
it, yes.
It's a red pole, not black.
صارت بول جديد.
Yeah, it's
صارت
not
بول
black.
جديد.
So it's a red color. So this is so I changed the location of my pole from here to here due to the add of this controller K. When I added this controller K and I feed my system, so now the overall system V over V desire has a new pole here. So I shift the location of my pole from here to here, and we know the effect of changing the pole location on the dynamic of the system. This is, we spent some time when we did system analysis on studying the effect of changing the location of the pole. And I told you this is very important for control engineers to understand the effect of location of poles on the transient response of the system. So now your new pole becomes here. Does that tell that the red system is faster?
Yes.
Yeah.
Yes.
Because if you are closer to the imaginary axis, you are slower.
بتكون slower فكل ما نبعد بتصير faster.
So now we answered the first thing we saw in theory in simulation, that increasing K will make the system faster. Here increasing K means you are going to go here and here more and more. So then your system will be faster and faster. Also, The other effect is on steady state error. So let's see the effect on steady state error. So looking at this, I will challenge you to do it yourself at home, but I will give you a hint. And we keep for
هو
just
ما بالنيوميريتور
مم.
هتصير تقريبا 1 عشان لو الكي كبيرة فصار عندك 1 فوق، وتحت الكي كتير كبيرة فالام صغيرة، الام على الكي انفينيتي فبيطلع almost 0 فبيطلع 1.
so
فالستادي ستيت الايرور بتصير كتير
very
صغيرة
nice. You are
بتصير يعني في اس ايكوال في ديزايرد يعني.
تقريبا. ايوه صح 100%.
yeah, very nice, very nice. So then, yeah, so that's my hand. You can do the calculation if you want, but yeah, I agree with you. So now you need. I'm talking about steady state error. So E steady state, which is E infinity, error at infinity. Here is my error. Error at infinity, if you want, limit when s tends to 0 of s E of s. If I want to use the final value theorem. Then my point is now what's E of s? What's E of s? E of s is equal v desired of s minus, so I'm saying n equals 0 of course in this exercise. So then
minus y.
minus, yeah,
V,
minus
V.
which is the velocity in this case. Okay, v of s. All right. So then my v desired. So assuming as we did in the simulation, actually we was considering step input as v desired. So what you will do at home. Okay, I have one trick I do usually myself to make things. If you want, you can learn this trick. Is to make the calculation easy. So there is one trick I do is I divide. My ultimate goal is here is I need to find E of s. That's my goal, and the steady state error function of k. And then you will find when k increase, E of s will decrease. So you'll find you end up having E of s function of k. You will do it yourself at home, but the trick I do, I divide E of s over v desired of s, which is the reference, because this will give me 1 minus v of s over v desired of s. And why I'm doing this? Simply, I'm doing this because v minus v desired, I already calculated it. I have it here. So that's why I say then this is gonna be 1 minus k over k plus b over m over k plus b s plus 1. So then later, then E of s, it becomes v desired. It's a step. What's the Laplace transform of a unit step?
1 over s.
It is 1 over s. So Laplace transform is 1 over s. Then I replace v desired by 1 over s. So I say it is 1 over s times 1 minus k over k plus b over m over k plus b s plus 1. So from here, I want you to continue it yourself. Would you think able to? So you need to put E of s in here and replace s by 0, or s tend to 0. Any question regarding how to find? And then you will find like a function. You will find E of s function of k, and you'll find like when you're increasing k, when you're increasing k, E of s will decrease. You want to do together or you do yourself?
خلينا
No,
نعملها
we
مع
will.
بعض دكتور مرة واحدة.
we do it quickly.
صح. Yeah please.
Then
طب بتطلع هي 1 هي k على k plus b لأنه بتروح الأس تحت
yeah,
بس نضربها يعني.
because so you get what Rami said. I will multiply this s by s. So then you will neglect
بتروح هاي.
each other. Then I will get having 1 minus k over k plus b.
over 1.
بس دكتور سؤال،
Yes.
هلا نحن حطينا اي اوف اس او الفي ديزاير اعتبرناها هي ستيب ريسبونس بلابلاس ترانسفورم صارت 1 اوفر اس يعني اللي حطيناها.
Right. صح.
يس
It's
يس
a unit step input. So Laplace of s is
يس
1 over s.
is 1 اوفر يس اوكي.
So then this is 1 minus k over k plus b. So if you want to take k plus b common, so k plus b minus k, which means b over k plus b. Okay, so let me directly write it, b over k plus b. So then this is okay. Then it is b over k plus b. Good. So what that tell you? If you increase k, your E of s will decrease. So that's why the steady state error will decrease. You get it? So maybe in that now, if you want, you think yourself, what if my input was a ramp? You could ask the question in this case in the exam. What if the input was a ramp, wasn't a step? What if the controller was not k, was maybe kp plus ki over s? Or what if it was kp plus kd or kds, like PD controller or PI controller? How this will affect the system? So you could do this study. Okay, and this question we ask. Let's go to the chapter. Here actually they demonstrated. Yeah, they found the gain, the tau, they find b plus k over m as we did. Okay. So in the preceding, the control was proportional to the error, called a p controller. We can add terms for the integral of the error and the derivative of the error, and we get the PID controller. Each term of the PID controller changes system performance in different ways. So now we learn the proportional, how it affects the system performance. So later we'll learn how the integral term will affect the system performance, how the derivative term will affect the system performance. Overall, how we could tune our PID. Okay. Any question regarding this chapter? Introduction to control and block diagrams.
لا كله تمام.
Yes, then I will go with you. We still have 15 minutes on very small chapter, which you will find yourself, you already know it. I'm talking about steady state error. Steady state error is something you know, but just I'll make it more structured. And system type is a new thing you will learn. But the first part of this chapter is something you are familiar with some slight difference I want you to pay attention on. Only minor things maybe you don't know in steady state error. Basically, you know steady state error with only one minor things you don't know. I will explain it to you, and usually students, even after explaining this, they still get confused one. So just pay attention on this minor things. You know all of those. Here is what I'm saying. I want to say, if I have it in different places, No, I don't have. Okay, it's all right. By definition, the error is, maybe I write over what they are writing here. By definition, here is a light difference. By definition, error is your reference minus your output. Always in practice, that's what we do in the simulation, right?
دكتور مش الاوتبوت مضروب بالفيدباك لازم يكون؟
Yeah. Look what we are doing here in practice. When we compute the error, I heard your question, Rami. You will find the answer yourself. That's the error, right? Difference.
يعني الفرق بين الانبوت وبين الاوتبوت طبعا.
Yeah, difference between input and output. R minus Y or Y minus R, doesn't matter. It's absolute value. It's all right. R minus Y or Y minus R. That's my error. That is my error. R minus Y. Always we're comparing the reference, the input to the output, because my ideal situation is to have my output follow my reference. So means I have zero error. Okay. So we saw it in simulation. So what's the trick here? What if I have, as Rami said, what if I have a dynamic of the sensor and my sensor is not one, as always. I have a sensor dynamic. So then this is not the error. When I ask the student where is the error, they tell me this is the error. And this is wrong. The error is still the same. If I ask you to compute the error on Simulink, in this case, you need to add maybe here summation block and put on it minus y and plus r, and tell me r minus y is your error, and you take it to a scope if you want. You see? Did you?
يعني هون قصدك انه السنسر عم بيأثر على السيستم؟
No, it's not influencing the system. The sensor
لكن...
is not influencing the system, but your error.
طب لكن ليش غيرنا الايه؟
Usually, when I'm telling you your error is here before, I was considering unity feedback. I was considering a sensor dynamic equal 1.
يس فهمت، بس قصدي انه نحن بنحط الايرور هي ان الانبوت ماينس الاوتبوت او الاوتبوت ماينس الانبوت.
Yeah.
بس قصدي انه
input minus output
انه لو
or
كانت
output
يونت
minus
فيدباك.
but this is not the input. This is not the output. Look to your mini project. The mini project we did. Look to your mini project where I non-canonical system. I introduce it to you maybe here. Wait, little bit. Non-linear. Sorry. Maybe faster if I go to Moodle. And now non-linear. I don't remember. Maybe faster if I go to Moodle and quickly, without letting you losing your time. Yeah. Please go ahead. Yeah, if you remember, I want to show you that video. So don't return back to it. Control system design. Your mini project was your mini project. Last milestone you did here. I told you watch this video from 40 to 1. Okay. And if you go to the video,
gain على
yeah. So look here. Maybe here. Yeah. Iyad, are you able to see my screen?
Yes, Dr. معه.
So here, because I'm taking sensor dynamic K, you can see.
Yes.
Then
Yes.
here I'm putting at your reference, I'm multiplying by the sensor dynamic as well, if you want to get this reference. So dividing by it. If you are here multiplying by, so I multiply by the same number here.
Yes.
Okay, so then I multiplied by the sensor dynamic. I multiplied by the sensor dynamic. Taking it here the same thing. If you want to keep this as the error, so then come here and multiply by the sensor dynamic. So then you put here your sensor dynamic. If you put here before the reference, as in the YouTube video I showed to you in your mini project, if you put here your sensor dynamic, then yes, you can take this as error, because at the end what do you have? I said error is r minus y. That's the definition of the error. Then here let me call it a. Okay, here is a. So a equal to what? Equal to r in this scenario minus yh, or minus ym. R minus ym, and ym equal yh. Okay, so here that's
okay,
a.
yes.
But if I have here h, assuming now I add here h to the r, so then what's a in what's new a?
صارت RH minus YH.
RH minus YH. So which is
يعني صارت كأنه H into error يعني
HH
ينضرب
R minus Y. Yeah, which is H times the error. Yeah, it's not the error. Exactly. So then here it's not the error, it's the error multiplied by the sensor dynamic.
Yes.
Yeah, so means
يعني HE.
proportional to the error. So assuming here H is simply gain.
Yes.
Then becomes this way. Yeah. So then, yeah, if you want to keep it here proportional to the error, then multiply here by the sensor dynamic. So you get a value which is proportional to the error. Otherwise, the error stay in the other. So they are equivalent at the end. You just multiply.
انا صراحه ما فهمتش شو الهدف يعني من هالموضوع، انه لما هي equivalent يعني دي ما فينا نعملها نعتبرها هيك بلا ما ناخذ
No, so what I'm saying and of and, that's the definition of the error. Input minus output, or output minus input. It's not the actual output, not the voltage of it, the output of the sensor. At the end, the output of the sensor is a voltage. Then if you want to compare, you can compare voltage with a voltage.
صح، ما هيك عملنا بالمايلستون احنا كمان لك حطينا كيه.
So you compare voltage of it. So you cannot say 4 meter in this case. So you need to convert the 4 meter to a voltage. So you put the sensor dynamic to convert the 4 meter to 0.4 volt.
هيك صار فينا نقدر مع بعض.
So then you are comparing voltage to voltage. Then you get an error, which you get a proportional to the error, which at the end it's an error. Proportional to the error. Proportional to the error, at the end it's an error, but different error. Let's say E prime. This is E.
Okay, فهمت شو قصدك.
Okay, then
بس ما بنكون جبنا نحن الريل ايرور يعني.
Yeah, the error is R minus Y. Then you just to pay attention about the definition of error. We end up here. يعطيكم العافية. Next time we'll start from here. Just now we fixed the idea. What's the definition of error? Next time I don't want to explain it. I will start as if you know that E equal R minus Y, and we'll start from there. Okay?
يعطيك العافية دكتور.
بدي اسالك شيء.
Yes, please go ahead.
في عندنا